Right, hello, I'm Nick. I'm trying something new. I will solve this second division in the first round, and I will try to explain what I'm doing. I'm a bit late, but that doesn't matter. So let's just start. So in problem A, we are given an integer k. We want to find the largest x between 1 and k not inclusive, such that x factorial plus x minus 1 factorial is divisible by k. Well, okay. I will need to swap those. Okay, I don't know how to solve that right off the bat. So let's just look at this expression. X factorial is x minus 1 factorial times x. So we can rewrite it as x minus 1 factorial multiplied by x plus 1. And we want this to be divisible by k, but we can just take x equal to k minus 1, right? This will be just k, so this is divisible by k, and this is the largest integer after k not inclusive, so this is just the answer, right? Okay. Weird problem, but sure. Wow, it's working. Who would have thought that I can subtract 1? In problem B, we are given a permutation and some number k. We want to sort the permutation, and in one operation we choose k numbers, then take them out, sort them, and put them in the back of the permutation. We want to sort the permutation in the minimum number of operations. So what I want to say is that let's look at the numbers that we didn't touch ever with our operations. They will move to the left of our permutation, like we always taking out numbers and then putting them in the end. So the numbers that we didn't ever take, they will be moved to the front, and their relative order should be the same. So we want to sort our permutation, so in the end it should be sorted. So if we didn't touch m numbers, those m numbers should be numbers from 1 to m, and they should be in the correct relative order from the beginning. Okay, let's find maximum such m so that numbers from 1 to m is in the correct relative order in the beginning. Well, then I'm saying that the answer is just n minus m. That's the number of elements that we have to touch, divided by k rounded up. Well, we have to spend at least that many operations, because we have to touch at least n minus m elements, and in each operation we can only touch k, so we have to spend at least n minus m divided by k rounded up operations. How can we make sure that it will be actually sorted in the end in that many operations? Well, let's just, in first operation, let's take numbers from m plus 1 to m plus k, and then make the operation with them. What will happen? We will take them out, sort, and put in the end. We can see that our first m numbers were in the correct relative order, and they stay in the correct relative order. And now in the end, there are numbers m plus 1, m plus 2, and so on up to m plus k. So now first m plus k numbers are in the correct relative order. And so we can increase m by k until it reaches n. Like in the end, we cannot overshoot. There is no number n plus 1, but we can just take the number k biggest numbers. It will be fine still. So we should just found m and then output n minus m divided by k rounded up. To find m, we will take an inverse permutation. Like for each number we will write down its position, and then we just like take the next number if its position is bigger than the position of the previous number. So it's like while we can take next number, while to the right of the previous we take it. And that's it. We're reading our permutation, but we only need the inverse permutation. So we can just read all the elements and then just say, okay, like for this element, it's on position I. I'm saying m is equal to 1, and while I haven't reached the end and the next element is to the right of the previous one, I can increase m, and now the answer is just n minus m divided by k rounded up. To round up, we need to add k minus 1. In problem C, we are given an array a of n integers, and we want to construct two permutations of length n, such that for every position ai is the maximum of two numbers in the permutations. Okay, let's we start with empty permutations, just n positions, and for each position we haven't determined the element, and we will put the numbers in the decreasing order. So let's say that we have put all the numbers that are strictly greater than x, and now we want to put x. Which positions do we have in our permutation? There are positions that are empty in both permutations. There can be positions that are filled in both permutations. Oh, they called P and Q, right? So, and we can have positions that are filled only in one of the permutations. Something like this. This is actually not possible because we have put the same number of elements in both permutations, so the number of positions where only P is filled in should be the same as the number of positions where only Q is filled in. So let's add this one. Okay, so now we have to put x in both permutations. What will happen if we put it in some positions? So if we put x here, we know that all the numbers that were filled in before are strictly greater than x, so the maximum is this one. So the maximum is P4. The same if we put x here, the maximum will be Q8. What if we put x in some position where both were not filled? Well, then the maximum will be x, because all the numbers we will put after that are smaller than x. Even if we put both x's here, it still will be x. So now let's look at our array A, in which we are given what the maximums should be. You can see that when we insert x, if we insert it on position that is not totally free, then the maximum in that position is already decided, and when we put it in the position where it was totally free, then the maximum in this position will be x. And that's the only way we can get x as maximum on position. Before that it would be bigger, and after that we will insert numbers that are not x's, so we won't be able to do anything. So if we have some x's in our array A, we have to get them now. So let's say that this position was x. What will happen? Well, I have to put x either here or here. It actually doesn't matter where I will put it. But what happens if x is on position which is partially filled or fully filled? That can't happen with our strategy. If that happens, we have already lost. So we are not allowed to put numbers in positions with smaller maximums. So this cannot happen. Yeah, we can have several x's in our array. If we have 3 or more, we have lost. Like it's just impossible. We only have 1x in one permutation and 1x in the other permutation, so only 2 positions at most can have x as maximum value on this position. Otherwise, both of those positions should be totally free, and we can put 1x in one of those and the other x in the on the other position in the second permutation. What happens if there are no x's in array A? Well, we shouldn't put x's on empty positions, right? So, but we have to put them somewhere. So what should we do? We should do something like this. We should put x's on positions that have bigger maximums. Okay, how do we find those? Well, we know them. Like we can just maintain, for example, the set of positions that are occupied only by P to insert something not necessary in Q, and the other way around for Q. So can we mess something up? Well, the answer is no, we can't. Like if the solution exists, on each step we will have the same number of free elements. Why is that? Well, because the number of positions we have to occupy by at least one permutation is just the number of maximums that are greater than x, right? And we know that we had to put all the numbers greater than x in both permutations, so we have put like 2 times n minus x numbers. So we know how many positions we can occupy, we know how many numbers we have put in. So on those positions, there are positions with 2 numbers and with 1 number. We can deduce the number of positions with 2 numbers from that information. And all the other positions should be evenly split by positions that only have number from P and only have number from Q. So that's it. Like we just do that. Process numbers from n to 1, maintain sets or like vectors. We don't actually like it's okay to take any position if we have choice. So we will have we'll maintain vectors of positions that are free only for Q, free only for P, and totally free, and depending on the number of times x appears in the array of maximums, we do different things that we have to do. Let's just write the code, it will be simpler to explain that way. Like it's just some ifs. So I have created array A, even though we don't actually need it. So N and A. Right. So we will have 3 positions for only for P, only for Q, and for both. Let's just order them in some way. We have same between tests. And for all the numbers, we will store the positions where it is maximum, and we also need to clear that beforehand. And now it's AI, but I only needed to store that it has maximum in position I, and from now I will only use this. Okay, so in the beginning all the positions are free for both permutations. Now we are iterating from n to 1. And we have to look like how many maximums for this number we have. If it is strictly bigger than, well, we have cases, right? 0, 1, 2, and bigger than 2. If it's bigger than 2, then we just say that it's impossible. We have to print something like no. And just check. So what if we have two maximums? Well, okay. In this case, if we have not enough free positions, we just say that it's possible. It's actually impossible to get here, like we can put assert false here, because we know that like the size of the sink decreases only when we put a new maximum, and the total number of maximums is n, so it cannot become negative. But like it kind of makes sense. Otherwise, we just take two positions from it. And put x on those positions in different permutations. So p of v is q of u is x. And now this position will be free for q, and this position will be free for p, so we have to put them in corresponding arrays. So positions free for p u, and at here. What if we have one maximum? Well, then we have to take one free position and fill it for one of the permutations. For the other permutation, we have to then put x in some position that is free for that permutation. For example, in the position we have just filled with x. So we can just take one position and put x there for both permutations. Again, this shouldn't happen, so we can just say assert false. Then take one position, put x in both of them, and now this position is completely filled, so we just don't do anything here. And here we have to take one position that is free for p and put x there in permutation p, and the same for q. If there are no free positions, then it's impossible. And this can actually happen. Otherwise, we know that the number of free positions for P and Q is the same. Well, we only increase them together, and here we will decrease them together. So we can say that positions for Q should be also non-empty. And now we take one element from each. And we're done. And after we have done our main cycle, we just print answer. This doesn't seem right. Yeah. On the first position we should have 5. What happened? Oh, right. I cannot just choose this. I have to put them where Max puzzles. Yeah, that was stupid. Okay, that means that I don't actually need this thing, so we can just say like this. And so this is max pos zeros, and this should be max pos zeros and first. Assertion failed false. Yeah, I don't have those things anymore. Okay, this looks right. So let's put assert here. Alright, it's actually happening when in the second test we don't have 2 as maximum, but like we can have maximums and still fail this check. And something like this. So we have 3, we will put it here, but then for 2 we don't have 3 positions to fill it in. Oh yeah, more permutations. That's a cool setting. So we are given a permutation. We can swap 2 elements in one operation, and we want to find the minimum number of operations to have exactly one inversion. So we have to not sort it, but have exactly one inversion. Okay, so obviously one way to do that would be to sort the permutation with minimum number of swaps and then do one swap of two consecutive elements to get an inversion. That is not bad, because if we can sort the permutation in k swaps, that means that we cannot get to one inversion faster than in k-1 swap, because otherwise we would be able to sort faster. So we know how to get answer k+1, and we know that the answer is at least k-1. What we also know is that parity of the number of inversions changes with each swap. You can check it. But yeah, it's a known fact. I set a problem about it. So we know that k+1 is a valid answer. So k is not a valid answer. Like, the parity of the answer is fixed. So we only need to check if we can do that in k-1 swaps. What is the, how to find k? How to sort the permutation in minimum number of swaps? For that, we have to think about the permutation is a collection of cycles, and each swap, if we swap two elements from different cycles, we will unite these two cycles into one big cycle. If we swap two elements from the same cycle, we will split this cycle into two cycles. Sorted permutation have n cycles. So if we initially have m cycles, and in one operation we can either increase the number of cycles by 1 or decrease the number of cycles by 1, we have to do at least n minus m operations to get to n cycles, and each of those operations should split one cycle in two. So how do we check if we can get to exactly one inversion with k-1 moves? Well, for a permutation with exactly one inversion, it has n-1 cycles, and one of those cycles is of valence 2, and it should contain two consecutive numbers. So again, if we want to get to n-1 cycles in k-1 operations, in each operation we should split one cycle in two, and in the end we should get to the situation where we have n-2 cycles of size 1 and one cycle with two consecutive elements. Can we do that? Well, we cannot merge cycles. So if two elements two elements are in two different cycles in the beginning, they will remain in two different cycles. So to succeed, we have to have two consecutive elements that are in the same cycle. If we do have those, we can make sure that they remain in the same cycle. It's not that hard to see that. So yeah, we just will find the cycles of the permutation, find the number, then say that k is n minus number of cycles, and then we check if there are two consecutive elements that are in the same cycle, then the answer is k-1, otherwise it's k+1. That's a nice problem about permutations. Nice educational problem. And the settings go I like it. We have our permutation shifted to 0 indexing. We will like ID the cycle, so we first say that for each element the cycle is not defined and the number of cycles is 0, and now we will traverse all the elements, and if the element for the cycle for this element is not yet decided, then we will find the cycle, and that is done just by traversing, going to the next element on the cycle until we have found all of them, and we will say that the ID of the cycle for this element is m. And we stop when we arrive at the first element, but it will only already have a cycle ID set, so that is how it's done. And now we're saying that the answer is n minus m plus minus 1, depending on whether there are two consecutive elements that are in the same cycle. Let's check that. If there are two consecutive elements that are in the same cycle, then the answer is n minus 1. Otherwise, it's m plus 1. Oh, runtime. Okay. I had some sort of. Let's see. So n is big enough. Clearing everything. Yeah, I have this assert. But what? Oh, it should be put back here. Yeah, that's a bug. Okay. Let's construct a test. It's not that hard. So what I need to do is I have to create a free position that is done by having two maximums. Then I have to spend it, but it won't be deleted from here. So it's something like this. Oh, cool. I cannot see it because of. Cool. Let's delete it. So it's no now, but if it's back here, yeah, it's free. Consider a permutation P. Sure. I have been doing this for 40 minutes already. Okay, so we are given a number n and a prime number n modulo which we have to calculate the answer. We're looking at all the permutations of length exactly 3n, and we can do the operations like sort the first two n elements in increasing order and sort the last two n elements in increasing order. It can be shown that every permutation can be sorted using only these operations. Let f be the minimum number of operations needed to sort, and then we have to find the sum of f over all the permutations. Okay, so this is a problem about a sorting algorithm, like kind of esoteric sorting algorithm. I think it's called Stooge sort. Let's try to Google it. Stooge sort. Yeah. So you can see that the algorithm works like this. Okay, if the value is larger, I don't think it's needed only for sorting an array of two elements. So if there are at least three elements, then we recursively sort first two sorts, then we recursively sort the last two sorts, and then recursively sort first two sorts again. This is a very slow algorithm, like it has complexity worse than bubble sort. Why does it work? Well, the recursive parts, we'll just assume that they just sort the part is needed. Basically, we are doing an induction on n, so it works for n equal to 1 obviously and n equal to 2 because of this. Now we can assume that we are in this step, and for all the smaller sizes it works. So when we do this recursive calls, they just sort the segments that we set to sort. So we can just assume that it says sort first two sorts, then sort last two sorts, and again sort first two sorts. Why does it work? Well, because after we sort the first two sorts, we can understand that the 1/3 of the biggest elements of the array are now in the last two sorts. Why is that? Well, either they were in the last 1/3 from the start and they will stay there, or they will be moved to the end of the first two sorts, and since there is at most 1/3 of them, they will be in the second sort, all of them. So after the first operation, the largest sort of the elements are in the last two sorts. Then after we sort it, they will be in the end. So they are on the correct positions. So when we recursively sort first two sorts again, we will get a sorted array, because like last sort is correct, and then we just sort all that remains. And it actually you don't have to have two sorts everywhere. We just need I think the sum of these three sizes should be like at least 2n or like strictly bigger, but it doesn't matter for our problem. In our problem, our array is of length 3n, and those are not recursive, they just do the actual sorting. So knowing about stooge sort just says us that it is always possible to sort in three operations. Like you can sort first, then last, then first, and the array will be sorted. Okay. We can actually see that it doesn't make sense to make the same operation twice in a row, because the second one will do exactly nothing. We know that so f of p is at most 3, and well, in most cases it will be equal to 3. We need to understand in how many cases it is 0, 1, and 2. Well, 0 is easy. It's the only permutation that is already sorted. How can it happen that the permutation can be sorted in one of those operations? Well, either the last sort should be correctly sorted, and then we just sort the first one, or the first sort is already correctly sorted, and we just sort the last. So okay, let's do some combinatorics. So in 0 operations, or let's say like f is equal to 0, that's one permutation. F is equal to 1. It is actually simpler to calculate the number of permutations for which f is at most 1. And then we will subtract this. So what did I say? I said that either the first sort should be sorted, there are 2n factorial such permutations, because for n elements we know where they are, and the other can be in any order. The last sort is sorted, but it can happen at the same time. So if both first and last sorts are sorted, then the middle sort in some weird order only. And like we added it twice, but we only need to add it once. But also there is already sorted permutation that shouldn't be there, but like we said that we're calculating number of permutations with f up to 1. F up to 2. Okay, this will be harder. So so we either first swap sort the prefix and the suffix, or in the other order. Obviously, the number of things that are sorted in the first and the second way are the same, but then we have to calculate the number of permutations that we counted twice, that are sorted in both ways. So, what does it mean to be sorted by this thing? Well, after we sort the prefix, all like the first sort will not be touched anymore. So we should put the right numbers here from the start. So all the numbers from 1 to n should be in this prefix. So when we sort them, they will become in this first sort, and that's enough. Like If that is true, then we will actually do that, and then we will sort the suffix, and it's all good. Okay, so what is the number of the things? Well, we need to we have the two n positions here. We need to choose n of them for these n numbers, then somehow permute them, and then permute everything else. So it's 2n factorial squared divided by n factorial. Okay, so now what we have calculated twice. We have calculated twice permutations that I mean what will be sorted by this and in the other order too. So the opposite property is that all the numbers that are greater than 2n are somewhere here on this suffix. So how can that happen? Okay, let's write something first, and then we'll see if we can optimize. We can iterate over number of the small numbers that are in the middle. Let's say it's k. So it will be sum over k from 0 to n. Now what? We have to choose those k positions here, and also choose n minus k positions here, which is the same actually. Now on this suffix we have only 2n minus k positions, and we have to choose n of them. And then we permute small, permute big, and permute everything else on the leftover positions, so it's just n factorial cubed. We only have to solve for one n, right? So that's enough to get accepted, right? Well, we can pre-calculate all the factorials and inverse factorials. Then we calculate this, and the number of permutations for which f is at most 3 is just 3n factorial, because that's all of them. And then we easily calculate how many permutations needed. Exactly 3, exactly 2, exactly 1, and exactly 0 operations, and then just calculate the answer. But I'm interested if I can do it better. Okay, let's try to write this in factorials form. So it will be n factorial here, and k factorial minus k factorial. Here is the same thing here. Now here it's 2n minus k factorial and n factorial, n minus k factorial here, and n factorial cube more. Okay, so n factorial in the fourth power can be just moved here, and we will get this divided by all of this. this is not helpful. I guess I have a better chance of coming up with some combinatoric meaning for this thing. I don't like this twin main ski on top. Okay, let's just get accepted, be boring. Oh, I can't use my min because the model is not fixed. I will have to remember forgotten art of using the operations with functions. Using an and mod. Now we have to calculate factorials and inverse factorials. Okay, now calculating the things. So this is okay. So it's add 2n factorial and then subtract n factorial. So f2 Okay, I can do that. And now I have to subtract all of those things. So what is it? N factorial to the fourth times 2n minus k factorial times inverse n minus k factorial to the third and inverse k factorial to the second. Okay. So it's n factorial to the fourth multiplied by 2 times n minus k factorial and multiplied by inverse factorial of k squared and inverse factorial of n minus k to the third. And f3 is just 3n factorial. Now at f1 minus f0 multiplied by 1 f2 minus f1 multiplied by 2 because it's the number of permutations for which you need exactly 2, and f3 minus f2 is the number of permutations for which you need exactly 3. Works, but I'm not happy about it. So problem F, well, small memory limit, interesting. We are given an array of positive integers. It's not a permutation. Wow. In one operation you can jump from I to j only to the right by paying mean on segment times j minus I squared. For all k, find the minimum number to get from 1 to k, and all the numbers are up to n. When I see squared, length squared, it looks like something convex. So let's understand what's going on. So let's say that we start in 1, which is x0, then we jump to x1, then we jump to x2, and so on, and in the end we jump to xk. So what is the cost? The cost is sum of mean on segment. So here we iterating from 1 to k. Mean on segment from xi minus 1 to xi aj multiplied by the difference, the length of the jump squared, right? So both ends are included in the minimum. Okay. Okay. So I can just jump everywhere. Then all of this will be just 1, and the cost will be like sum of minimums of 2 consecutive elements, which is not bad, right? Like all of the numbers are at most n, so this is at most n times n minus 1, right? Like we have n minus 1 segments, each of them is at most n. So this is some reasonable cost. And like when I want to jump to length when I want to jump L, I can always do it in at most L times L minus 1. If L is jump, like here I'm jumping on n minus 1, so it's L times L plus 1. Okay, cool. But if I'm doing this jump right away, then I will pay minimum times L squared, which is like a lot. So this is L squared plus L. So if minimum is at least 2, then this doesn't make any sense. Like this is cheaper. So that means that, well, and if I'm doing some jump, I can replace it by the sequence of smaller jumps. So that means that I'm either jumping when minimum is equal to 1, or I'm only jumping with by 1. Okay, cool. So if we are doing DP, obviously we can solve it in like some polynomial with DP, just what is the minimum cost to get here, and just try all the jumps and make them. Okay, so when we are doing this DP, if I want to jump to this point, what should I consider? Well, I should consider the jump of length 1. And also I should consider the jumps that have minimum equal to 1. So I will find the closest one to the left of me, and now from all the positions to the left of this one included, I can make jumps that will cost me just square lengths. Oh wait, this is not true. This n is the limitation on AI, and if I'm thinking about jumps of length L, the elements can still be big, so I can always do it in L times n. Okay, good catch. So it makes sense to make this jump only if min times L square is less than L times n. So this is not correct. This is not correct. This is not correct. Okay, so minimum should be at most n divided by L. What does that mean? Well, we can obviously iterate over L up to like square root something and consider all of those jumps. And for L greater than square root of n, minimum should be at most square root of n. So, like, instead of doing this, we will consider the previous positions of numbers up to square root of n, and we will have like this zones, right? So I'm jumping here, and like when I'm considering from where I'm jumping, if I'm going from right to left, like my minimum will decrease, and like I will have these segments of equal values, and then I will get a decrease, and so on. Okay. Oh, yeah, we can also say this thing. If I want to jump from some point to some point, and minimum on this segment is not in one of the ends, like minimum is somewhere here, then it's always better to, instead of this jump, do these two jumps, because for both of these segments minimum is the same, but the sum of squares of those lengths will be less than square of total lengths. So yeah, for all the jumps, minimum on segment should be in one of the ends. And like, even if one of the ends is minimum, if there is the same minimum somewhere inside the segment, we can still do this split. So it only makes sense to do the jump if one of the elements on the ends is a strict minimum, like it's strictly smaller than everything between those 2 points. They can be equal, so it's not a strict minimum on the segment, but it should be strictly smaller than everything between. Okay, so now using this, so we know that one of the ends should be a strict minimum, and this should be true for jump to be considered to be good. So either, well, this basically says that mean multiplied by L is at most n, so one of them should be at most square root of n. So if length is at most square root of n, we just iterate over all such jumps. And for minimum smaller than square root of n, we will just iterate over all the previous occurrences of those numbers, because if we take not previous occurrence but one before that, there will be a midpoint which is not worse. Or like maybe the minimum is this, like the right border. That might be a problem. So if the minimum is left border, then yes. But if the minimum is the right border, it kind of feels like I should just be able to do all these updates. Like I'm saying that total number of interesting updates when the minimum on the left is n square root n. So the total number of interesting updates when the minimum on the right is also bounded by n square root n. So I'm just doing them in like the most stupid way. I'm just running to the left until I encounter smaller or equal number, and then I stop. I can do and I do it only if this element is at most square root of n. Right. And that's n square root of n, because for each number between 1 and square root of n, in total I will, like, for this number I will run at most to the previous occurrence of this number, so the total length of all the segments for this particular number is at most n. So it's at most n square root of n. Cool. So the solution is very simple. I don't even need to get min on segment, because I know that in all the reasonable jumps, minimum is on the one of the ends. And if I do a jump for which it is not true, I'm doing that jump with bigger cost, but it doesn't matter, because it cannot improve the answer because I'm doing this jump with the worse cost. But it is not needed for optimal solutions anyway, so I can just say that the cost is actually like minimum of two bordering numbers times the square. So yeah, the solution is like really stupid. Like the code will be so simple. I don't need any data structures. So yeah, when I was coming up with a solution, I thought that I will store like the last occurrence of each number and do jumps from them, but instead I can just like I'm doing the transitions when the right border is the minimum, I'm just running until I stop. I can do the same like with forward transitions from the left. So when I'm staying in the left, I can do all the forward transitions from this place. So I need square root. Okay, so first I need to do transitions from the like to this point. So there are transitions with length up to square root. And if this element is smaller than square root, then I'm running to the left I'm making the corresponding transition. And if this element is at most me, I stop. I don't need to do these transitions further. Now I have the correct value of dp, and again, if this element is smaller than square root, I will run forward now and do the same thing but with forward transition. Like, so I'm updating dpj from I. This can actually stay the same. And I stop if I found a bigger element, and that's it. I have calculated everything, all the dp values. Yeah, the samples will be not very helpful because I have constant b, but like this should be correct, right? This is a very nice problem. This is crazy. Seriously? Okay. Okay, cool. Sure. Thanks for watching. Bye.